right, so we're here today to talk about a really interesting bridge project that the Michigan DOT just completed, late last year. Relatively small bridge, but it's got a lot of interesting aspects to it we're going to try to share with you today. So I'm going to lead it off and talk about some of the site constraints and some of the reasons why the bridge was constructed the way it was. I'll talk a little bit about the bridge design itself. It's a network tied arch, and we'll explain a little bit of what that means and why that's important. Matt's going to talk about some of the ABC alternatives, accelerated bridge construction alternatives that we evaluated during the design phase. And then Matt and John are going to collaborate to talk about the bridge construction itself and then the move from the staging area into its final location. And then hopefully we'll have some time for question and answer at the end. So there's the three of us. I'm the National Bridges and Structures Practice Leader for HDR, and I was also the engineer of record for the 2nd Avenue Bridge. John is the taller gentleman standing next to me in the photo, and Matt's the one who doesn't appear to actually be on the construction site. Not sure why that is. I think he was there a lot more than either John or I, to be honest.
I took all the photos.
Exactly. Yeah, John was, exactly. Matt was the one taking photos, just like Dad on vacation. Mm-hmm. So the I-94 corridor in in Detroit, is a system that was built in the 50s and 60s. It's in the process of being replaced over time. Some of the bridges have reached a point of deterioration where they simply won't last long enough to survive until the rest of the highway corridor is replaced in the coming years. So MDOT developed what they called an advanced bridges program to replace the 8 worst bridges before the rest of the project could move forward. We did look at the feasibility of using ABC for a number of the projects. And then because this is really a $2 billion or more corridor reconstruction project, they were looking for some type of a signature structure, something that would make sort of a visual statement, to kind of highlight the project. And fortunately, the 2nd Avenue Bridge, I think, checked all of those boxes. When we started the project, MDOT described a couple of the most important goals. I mean, obviously, from a practical standpoint, minimizing traffic impacts to I-94 was vitally important. This is a corridor that carries about 175,000 vehicles a day. So, and it's one of the main arteries into one of the major cities in North America. So it was very important to minimize traffic impacts. And they also wanted to minimize the need for any throwaway work, any type of temporary construction that would be built today and then demolished in the future. And the reason I say that is in the future, the entire I-94 corridor is going to be widened and shifted about 40 feet north of where it currently is to better suit the alignment. And so we looked at a variety of conventional bridge structures at the beginning that would have a pier constructed in the median today, and then shifted to the new median at some point in the future, meaning you'd have to demolish the pier that was just constructed a few years earlier. So that was something that was immediately set aside. The bridge itself is located right in the middle of the Wayne State University community. So there's students on either side of the highway that need to get back and forth from their living accommodations to campus. So it was very important for them to have a safe and attractive pathway to get to campus. I brought in a lot of stakeholder involvement, not only from the university community, but the city of Detroit. You know, anytime you've got a modern structure, and especially near a university campus, having pedestrian and bicycle access is going to be very important. And the city was really looking for a park-like type environment. It was almost treated like a park that would happen to carry a few cars and trucks every once in a while. So that's what we were looking for, a somewhat wider structure and something that was open to the sky. They really liked the idea of eliminating lateral bracing between the arch ribs. That had not only a appeal from a visual and a experience standpoint, but it was also very practical, and we'll talk about that in a minute. So the bridge itself has separated lanes for vehicles, bicycles, and pedestrians on the sidewalk with green space, planter boxes, landscape medians. Like I said, basically a park that happens to carry a few cars once in a while. I mentioned that the highway is going to be widened in the future. One of the things that we felt was really important was having a clear span bridge that eliminates that center pier altogether. We also needed a way to build a shallower structure that would reduce the need to raise the profile to maintain vertical clearance over I-94. So that would reduce impacts to the surrounding streets on either end of the bridge. There's a historic property that's I'll explain here in just a minute why that's important. And we did look at some ideas for using self-propelled modular transporters to move the bridge into place. And we'll talk about why and how that was done later on. So an early rendering of the project, you can see the bridge itself, some of the landscaping ideas, and you can compare that to the existing bridge or the original bridge that was there when we started construction. This parking garage to the right-hand side, that's going to be very important, and we'll talk about that too. This is an old motel that was significant, and then there's a building right here that was a very important historic artifact in the city of Detroit. It's a historic recording studio that was basically the foundations of Motown music. And to the city of Detroit, that is a very, very important historical landmark, and that could not be touched during the design. So that really impacted a lot of the things, a lot of the alternatives we had for constructing the bridge. So, as I said, the bridge is a skewed, unbraced network tied arch. So what that means, if you look in plan view, the bridge deck is not a rectangle. It's got two acute corners, two obtuse corners, and the whole idea for skewing the bridge was to accommodate the frontage roads on either end of the bridge and the adjacent properties. And that means that historic recording studio, no lateral bracing between the arch ribs, which is somewhat unusual. There's only a handful of unbraced tied arch bridges in the US. And the network nomenclature, that's talking about the orientation of the cable. Instead of being vertical hangers, as has traditionally been done with a tied arch bridge, these are crossed diagonally. And there's some real structural advantages to that system, basically providing additional redundancy and stiffness and allowing us to reduce the depth of the structure even more. And when we talk about a tied arch, what we're saying is that the deck itself serves as a tie. It keeps the ends of the arch ribs from spreading apart laterally as the deck is loaded, as the vehicles are passed over the bridge. So that's a big advantage from a structural standpoint. But the other thing it does, it allows the entire bridge superstructure to be freestanding. So we can build the bridge in one location, pick it up and move it to another location, and it remains completely rigid and self-supporting. So project site, like I said, downtown Detroit, if the Wayne State University campus is kind of the lower side of I-94. This is that parking garage I was talking about a minute ago. That historic recording studio, you can see, is right near the corner of the bridge. So that really dictated not only the bridge alignment, but also how the bridge would be constructed. And the bridge is actually much, much bigger than the existing corridor, much longer than the existing corridor was. So there really wasn't a great way to build the bridge in place. We looked at different possibilities of building the bridge somewhere else and moving it into place. And really the only feasible place to build the structure is in this parking lot area, what we're calling a staging area. It was a university parking lot. Wayne State is largely a commuter school, so there's an awful lot of students that park, and faculty members too, park there during the day. The I-94 corridor, as I said, was built in the 50s and early 60s. It's a depressed freeway for a large portion of the corridor, and with a very low vertical clearance. In our case, about 14.5 feet of vertical clearance over I-94. You can see evidence on the previous bridge of numerous overhead vehicle strikes. And so that was one of the other design considerations, was a structure that could be resilient to these types of vehicle strikes and repairable if it was to be struck in the future. The other challenge to the site is a 3 to 4 foot grade difference between eastbound and westbound I-94. And the reason that's important is if you're thinking about trying to roll the bridge across from one side of the freeway to the other, now you have to do something to accommodate that elevation difference. So the solution we came up with is a 245-foot span network tied arch. So you can see the diagonal hangers, indicating a network type structure. The tie itself is not just the deck, it's the post-tension concrete tie girders that connect the two ends of the arch ribs together. That's a rendering of the bridge prior to construction, and you can see why it looks a little bit longer really than would make sense for the current alignment of the freeway. And that's all because of that future widening and alignment shift that'll take place down the road. Skewed 18 degrees. That in itself is not a big challenge for a conventional bridge. It does complicate the details quite a bit for a tied arch type structure. The other thing that we had was an asymmetrical vertical curve. So basically what that means is that every single floor beam on the structure had to be slightly different because the skew and the vertical curve worked together so that all of the elevations were different from one side of each floor beam to the other. Just to give you a sense of how big the bridge is, here it is overlaid on top of a football field, roughly 2/3 the size of a football field. It's always, I think, easier to recognize the scales of these types of projects when you can lay it on, something to compare it to size-wise. So why is a network arch such an improvement over a conventional tied arch? It's much more efficient than a traditional tied arch bridge. The incline hangers really reduce the moment and shear forces in both the tie girder and the arch rib. So you see the figures at the bottom of the screen. Those two bridges are identical in every respect except for the hanger configuration. Everything else is exactly the same. And you can see that the forces in the tie girder and in the arch rib are reduced by a factor of 5 or 6 simply by converting to a network system. That allows us to make the hangers, mix the tie girder and the arch ribs much, much smaller, more efficient, and quite honestly, more visually attractive as well. And they also provide additional redundancy to the overall system. Just a couple shots of the tie girder during the fabrication and installation process. You see the trapezoidal steel box girders. It was all welded construction to form the box. And then the hangers themselves are attached to an internal system, and the hanger connection plates are simply passing through a slot in the bottom flange of the box girder. And you can see on the left-hand photo how they're penetrating through, and then the pin connected hangers are attached to those during construction. And there they are right there. The hangers themselves, 3 1/8 inch diameter structural strand, galvanized. Initially, we looked at galvanizing the entire structure during the design phase. And after some testing at MDOT headquarters in their materials lab, we decided it was actually better to go with a very reliable and predictable paint system. We had some concerns about the potential for bolts and those internal components being loosened by the hot dip galvanizing process. So at that point, we just went with a painted system that everyone was comfortable with and MDOT had used with great success in the past. As I said, the post-tensioning system, both the tie girders and the end diaphragms are made with post-tension concrete. Really, the only reason those arch ribs can remain vertical without lateral bracing between them is the post-tension end diaphragms. That's where that lateral stiffness comes from in the system. So the tie girders had 12 19-strand post-tensioning tendons. The end diaphragms actually had 11. And then the base plate at the ends of the arch ribs were post-tensioned down to the concrete knuckles as well, with 20 bars around the perimeter of each base plate. All right, and with that, I'm going to pass it over to Matt to talk about the construction process.
All right, well, thank you, Mike. Here, I'm just going to get this up. So as you can imagine, very complicated bridge. The construction engineering is a very significant part of the project. So just talk a little bit. I mean, this happened during the design phase as well, but it all ties together. Just some of the ABC alternatives that were considered, and really, building it off site and being, up above the freeway, above grade, really made sense to do an SPMT move. So looked at doing kind of three different options. You build the whole superstructure, move the whole thing into place all at once, deck, all the superimposed dead load. Downside that is it makes it really heavy. So kind of the in between there is you could build a skeleton, and this is what we ended up doing. Get the floor beams, arch rib, tie girder, diaphragm, not the deck, and then move that, and really just kind of help save the weight. Or there was another kind of out of left field idea a little bit, I'd say, trying to do panels where you could say do one arch and rib and tie girder segment, and didn't do the other, and then bring in the floor system and things. Didn't end up going that way. And I should probably take a step back too. And all these were using SPMTs, and for those who don't know, it rolls right off the tongue for us. But self-propelled modular transporters. They're more or less a bunch of linked hydraulic axles. They can move in incredibly large amounts of weight. These things get used all over the world for some really unique projects, not just in the transportation industry, but other industries as well. Really cool stuff. So what we ended up doing was just moving the skeleton. So the abutments were built in place, and you can see that on the right. And then a very early picture on the left of the skeleton being fabricated there in that parking lot. Now, obviously, any signature bridge, as you can imagine, sometimes in the life and times of a bridge, as one of my professors used to say, the most critical time in that life is early on in construction. Depending on the configuration and how things go, that could be the most critical load that bridge will ever see. So certainly something that wanted to be accounted for during the design. And how are you going to do this? This is pretty unique work. So there was a lot of, so to not be that engineer that thinks they know everything about construction, obviously there was a lot of one-on-one confidential meetings with the different heavy movers around the country and the world, really. Just see how they would do it. How would they pick up the structure? Where would they pick it up? Those types of questions. And scheme was came up with during the design phase that at least two of each of the movers could do, just to make sure that the bids would stay competitive. And then this was used to estimate any locked-in stresses from the construction phase. So this phase that sequence that came up with during the design phase involved picking up the arch, the whole superstructure skeleton from the arch itself, kind of inbound of the knuckles. They used temporary end diaphragms in this configuration to keep the weight down, and it would pick it up, called that handbag configuration, and then at that point drive it over to I-94, where it could just be set down onto a tower that would be supported by other SPMTs to then carry it the rest of the way across the freeway. And because this was not maybe the most ideal way to lift up a structure, it did drive a lot of the permanent geometry, particularly just trying to keep the member sizes as small as possible, really just trying to keep that weight down. Of course, knowing that the contractor could likely come up with another way to do this, a very detailed special provision was developed requiring the contractor to have an erection engineer and their own analysis and procedures, really backing up everything that they'd proposed to do. And kind of as expected, they they came up with something a little different, not terribly different, but a little different. The main change really came from they didn't want to support the superstructure off of the arch, but they wanted to pick it up right underneath the knuckle, right under the centerline bearings for the permanent condition, which structurally that's great. It actually even allowed those end diaphragms to get poured ahead of time, which is good for minimizing impacts to traffic in I-94. Really, I'd say the complication of this method came from how do you make that handoff? Now, you guys can see my mouse pointer here. If you look right here in this picture, this is called the skid shoe that Mammut uses. And basically what they ended up having to do when they drove the bridge up to the freeway, they then had to slide it or skid it on a track over the abutment to pass it on to the tower supported by SPMTs on I-94. To then drive the rest of the way across and then skid it again one more time back onto the abutments before it could be lowered. So for those playing the accelerated bridge construction game at home, not only did we have an SPMT move, but we also had a slide. So we're claiming some bonus points on that one. The one thing that's I like to note too is the erection plans and calculations and all the information that went into this procedure was about 1,700 pages. And anyone who's run a structural software knows, oh, that's nothing. I can print out 5,000 pages out of Larza, you know, no big deal. But this was actually 1,700 pages of the pared down version. This was all very relevant information that had to get reviewed. It was not just pages and pages of computer output. So it was quite an effort to do that. And in order to do that, it took more than one person, obviously. You know, HDR was the engineer of record for the superstructure. We were very involved in reviewing it. MDOT and their different, you know, construction, material staff were also very involved. And there actually was an independent peer review engineer. Parsons was brought on. I'll give them a lot of credit. They did a great job helping everyone out, bringing some good outside perspective to the project. And everyone worked together with the erection engineer to really just, you know, sort everything out. If anyone had a question or thought they saw any risk, you know, we got everyone on the phone and we talked about it. A lot of smart people in the room, or the team's call, I guess maybe you could say. But the teamwork really was invaluable. We may have sung Kumbaya once or twice, but it really was a highlight of the project, and just from a career standpoint of getting to work with some top-notch engineers from several different places. As part of this, you know, we did, in construction, developed 3 independent finite element models between HDR, Jansen and Spons as the erection engineer, and Parsons as the QA engineer. The HDR one, obviously we had them from the design phase that we then updated for the contractor's means and methods. And we had regular team meetings to hash out differences in the modeling, and just comparing notes. You know, there was discussion too, you know, the technique of where did you put that imperfection in your arch to get it to buckle, or the knuckles, how did you model the knuckles? That was a lot of conversation, actually. You know, did you use one massive, really stiff concrete member, or did you use some smaller but still stiff concrete members connected by rigid links? And you know, everyone being engineers kind of went their own way with it, but at the end of the day, there was concurrence between all 3 models that the bridge was going to be okay. And that, I think that gave, you know, certainly gave the warm and fuzzies to a lot of the people on the team, knowing that everyone came to that same conclusion. And, you know, to be engineers and continue to, you know, cross the T's and dot the I's, you know, prior to the move, we wanted this thing planned out to the letter. And there's another document, not quite as long as that first one, but really detailed everything about the move and the procedure, each step by step. You know, who's the superintendent and operators on site for the contractor. Here's their phone number, so you can call them. Who's you know, drawings, calculations, a lot of detail on a monitoring plan, which I'm going to talk about on the next slide. And we even actually all got together 1 month ahead of time at the Detroit TSC, which is their regional office in that area, and just really talk, you know, walk it through who's going to do what, how's this going to happen. And it was really valuable because we did, you know, shake out some loose ends during that meeting, and it took all day. It wasn't a 1-hour call. One thing I do like to mention too, just in terms of accelerated bridge construction, very early on in the construction phase, the contractor did have a VECP concept that they wanted. It ultimately was not accepted, though it's worth mentioning because it was just a really good example of some outside the box thinking. And they wanted, instead of doing the move, they wanted to build the bridge superstructure in place over I-94. However, to avoid the traffic impacts, particularly forming and curing that tie girder, they wanted to use precast segments and post-tension them together. Now, ultimately, this was not accepted, just kind of it was a lot of redesign and a lot of shifting of liability and risk to the contractor and away from MDOT and HDR as engineer of record. But again, it was a neat concept. And theoretically speaking, and it didn't get, you know, vetted through all the way through, but it would have been about the same week-long closures on I-94 that it also took to do the move. So just want to also touch on the monitoring during the move. This was a very critical thing. It's we got a several $1 million bridge. It's 5 million pounds, and we're going to move it, and we really want to make sure we don't break it. That'd just be bad for everyone involved. So we used 2 systems. There was a robotic total station that would shoot the relative distances between the each of the yellow squares you can see on the screen. Those were the different nodes. And also 2 electrified wires strung between opposite corners of the bridge that were constantly monitoring. And it was agreed through the whole project team that the worst thing that could possibly happen to this bridge is that one corner would get out of plane relative to the other corners, whether the hydraulics failed and it settled, or it went over a bump or something. But that twisting of the superstructure is really what we were trying to avoid doing. And the bridge was designed for up to 3 inches of out of plane movement at any one of those corners, and things would be okay. So as part of the monitoring, they established, I call them like a green, yellow, red light values. And so relative to that settlement of or out of plane movement on any corner, 3 inches would have been the red light, all stop. We got to make an adjustment. 2 inches was that yellow light. You're getting close. You probably should make an adjustment at this point. And based on those limits, we also out of the models were able to check basically not just the 2 corners, but if you took that model, you dropped one of them, saw how the structure deflected, that's how the relative distances measurements between the nodes were developed. And with this very thorough communication plan between the erection engineer and the guy watching the monitoring system, they actually got to be really good buddies on site. They were side by side for at least half of the time we were out there. So with that, I'm going to stop sharing. I'm going to turn it over to John, and I'm going to let him talk about the construction phase.
All right, there we go. Can you hear me, Matt? All right, you're muted, but I saw your lips move, and I'm assuming we're on the right screen now.
Yeah, looks good, John.
All right, good afternoon, guys. So yeah, we're going to walk through the construction process. We're going to keep it pretty limited on the overall construction process, as it ended up taking us 3 years, which is 2 years longer than we anticipated. And our therapists have said it's best not to talk about it to make us feel better about ourselves. So we're going to just kind of get into construction, and it's not letting me. There it goes. All right, so this is early on in the construction phase, but the first question is, what do you do with a 5 million pound structure in a parking lot? Because it clearly can't sit on grade, and at some point we have to be able to get underneath it with SPMTs. So the first stage here was to put in basically temporary abutments. Each of those A-frames in the 4 corners under the knuckles are sitting on driven pile. The rest of those supports are actually for the floor beams, and those are just sitting on reinforced concrete slab. Here is our floor beams up in the one picture, and our arches on the sides there. These are the original time that the floor beams were in Wisconsin. One of the trademarks of this project is every step of the way something was a hiccup. These beams arrived on site before we realized each of those hanger plates that's supposed to be at a very unique special angle due to the geometry of the bridge and the angle of the hangers coming in was actually wrong. They were all fabricated on a flat surface, and so all but a couple of the beams actually had to make a trip back to Wisconsin to be have all those bent plates there that you can see in the lower picture in the middle. The connector plates all had to be rebent, and everything had to be reshaped and then sent back to Michigan to get re-erected. So here we go. Here's a picture of them up on their temporary supports. I do believe this is their second trip back to Michigan. So you can see there that obviously each one's sitting on a floor or on these temp supports. Unfortunately, because they had to go back and come back, another problem we found is really we had to end up making custom shims for each one to get them to line up. And so what you'll see at the top of those temp supports and little uprights look like a football goalpost is actually a custom milled white oak shim. So basically a bunch of really custom oak wood blocks. All right, so obviously, one of the big things that we learned going into this project was that 8,000 PSI mass pour concrete that had to act like a self-consolidating, but couldn't be self-consolidating. concrete was going to kind of give us a bit of a headache. So we decided to put a mock-up in the plans. The mock-up was actually first one paid for by the department, the rest paid for by the contractor. So you can see here, this is some pictures from one of our earlier ones. The first thing we learned from the mock-up was although the steel spacing designed in the plans met a lot of industry standards and things like that, our contractor's own capabilities were limited. So we redesigned the steel from 50 KSI to 60 KSI to 75 KSI rebar. Obviously in the mock-up, it didn't really matter what strength it was, but that changed the spacing. And you see all the orange squares, those are spots they're thinking they might put their chute in for their pump trucks, things like that. And so they went ahead and constructed the mock-up. Each knuckle had to be built in 2 parts. So really most of what you see there is the bottom part. And then once it was poured, you'd be putting in the anchor plate and things like that for the post-tensioning rods at the end of the arches. Unfortunately, the first mock-up did not go well. And as you can see in the lower right-hand corner, that's what it looked like. At the bottom of the knuckle, we had consolidation issues. We also found some voids in other places. You can see in the middle picture that the top to bottom just didn't form in correctly. There's a number of problems. So at the end of the day, we ended up making 3 bottom halves and 2 top halves. So the mock-up paid for itself a couple of times over. One of the things that was also had to be done was this concrete. The initial mix they picked just wasn't getting the job done. And so they wanted to take a modification. They brought in MJ2 to help out with that, along with CTL. And yes, in the middle, that looks like a J-ring test for SCC, but it was not SCC concrete. But we found that pushing the slump limits to the limit of non-SCC, we needed to have some other tests to qualify the mix. And so we ended up doing some mock-ups on different size mock-ups. You see there on the left side, the testing in the middle, and then obviously your final product on a mock-up on the right. One of the interesting things that we've figured out is that we've actually poured more concrete in trials than we actually did to make the bridge. And the bridge is each knuckle is 200 tons of concrete, and each tie girder is 200 tons of concrete, and each end diaphragm is almost 300 tons of concrete. And yet we have, we've actually poured more than that we threw away. Here's the mock-up. We actually went ahead and cut it open at the end. And there you are. We end up rope sawing it in half. And as you can see from the pattern there's no consolidation of aggregate. There was no open paste areas, no large air bubbles. So it let us know that we did have a successful mock-up. And then, like all good concrete elements that are successful, we decided to break it up and throw it away there in the lower right corner. So actual knuckle pours. Again, we had to pour the tops and bottoms. So there on the left, you can see one getting ready to start pouring. In the middle there, the mud's in the forms. We are constructing that bottom half, which again, nothing on this bridge was level, nothing was straight, nothing was flat, everything's curved, everything's different grade. Even the 2 arches are at different grades. So it's a real nightmare, to be honest with you, to pour mud this way. So on the right-hand side, though, you'll see the top half of the knuckle, and we ended up having to do a mock-up especially just for that, because we kept finding, obviously in pouring like that, you're gonna have nothing but bug holes, which are created by water and trapped water and air. So we ended up using a fabric material that our project down the road at the Gordie Howe International Bridge had found to help them with their slope faces. And it just basically wicks the water away from the surface, which gave us a little bit better finish. And we were able to actually successfully finish 3 of the 4 knuckles. We still had problems with one of them with a blowout, and so we had to do some significant grinding and patching on that one. And then after that, after the knuckles were poured, we went into tie girder pouring. And then you can see here, this is actually the first tie girder on the left. Everything went okay. The middle picture, unfortunately, was our second tie girder, where we had some problems with some material that came out too stiff to actually get into the tie girder, and so we ended up having yet another delay while the contractor and Western Michigan University did some MIRA scanning and ended up having to scan the entire tie girder to look for voids to make sure that we didn't have any problems that wouldn't have found until we started loading the structure. So then that brings us to arch erection. Now, this may seem simple when you first look at it, but arches are shipped on nice little trucks, and they're level the whole time. And then when they got there, the one end to erect it has to be 32 feet higher than the other end. And when our contractor went to erect it, the clamping system that their engineer had designed did not hold, and we ended up taking the paint right off the top of the arch as it started to slip at about 16 feet off the ground. So we convened. We had a lot of billable hours for a lot of really smart engineers. And after thousands of dollars in engineering fees, we came up with a couple $100 green strap and a bottle jack. And ta-da, we have positive connection, and now we can erect the arch without it slipping through our hangers. And that's what you get to see on the right-hand side. And then we had to just thread 22 needles at the same time with our post-tensioning bars and there are post-tensioning ducts, and there we go. Obviously, then we have to set the crown pieces. Again, because of our tight spacing, we really could have used a third crane to manipulate this process. And unfortunately, we only had the room for two. So it became yet another unique step in the process that took way longer than we probably should have. But we really did manage to get that crown piece in place. And as Matt showed you that arch earlier, there is no room for a person to get through there, but yet someone did. And I don't know where they found this gentleman, but he did manage to squeeze through there to get inside to work on some stuff, and then and then crawled his way back out of the crown piece. So kudos to him. Here we are setting the last of the two crown pieces. And as you can see this from that parking structure Mike pointed out, we get some great photos from up there. The bridge is in place, the arches are in place. We have one duct at this point in each tie girder post tensioned to compensate for the load presented or implied by the arch. But now we're going to have to go ahead and post tension the rest of stage one so that we can get those tie girders to take off and the hangers to fit. So we went into post tensioning here. The original design had 12 ducts, 6 for load, 6 for potential future usage if we had an impact of some sort or something like that. Unfortunately, we turned this bridge into 90 feet wide for 20 feet of roadway with 2 raised sidewalks, 2 bike paths, 3 raised planter boxes, and a partridge in a pear tree. And at the end of the day, we ended up using all 12 ducts. So stage one was the remaining 5 ducts of stage one were done. We actually did another mock-up here. It's quite common if you haven't done any large-scale post-tensioning, it's quite common to do a mock-up. And a lot of contractors try to talk their way out of it because it's not needed, we're really good. Luckily, the department stuck to our guns and insisted they do the mock-up there on the left, and it actually, again, paid off because we found out some possible places we needed to check, and we were able to change the process for the burping and all that of each of the ducts to get it to consolidate correctly. And so there in the middle, you can see the mortar mixers, and on the right are just some of the tests we're running and overflow to make sure we get all the air out of the ducts. All right, so then comes hanger installation. Each of these hangers, if I remember correctly, the upper socket is just under 400 pounds, the lower socket is just under 500 pounds, and the cable weighs in at 20 pounds per lineal foot. So even the really short one wasn't exactly maneuverable. So we had to bring in the contractor. CBSI did a fantastic job. They came up with these custom Cs on the left, you see, to kind of allow the crane to reach around the arch to start installing the cables. And it took us a couple of weeks to get them all in. But obviously, once they're in, then it's time to actually get them to fit and to put the load in them. So we needed to get initial load of 120 kips per cable. So we got 2 60-ton jacks right there on the 2 opposite corners. You can see us putting in shim stacks there. A valuable lesson we learned here is one, your lower hanger needs to be milled, not cast. It needs to be milled, so it's a nice smooth surface. And honestly, if you hot dip galvanize 1/8 inch and 16th inch shims, you're going to end up with potato chips that just don't fit in straight. So we had a lot of hand custom making of shims. There were some very colorful words used, and just a good old time for a few weeks of fighting to get each and every one of these at right where we wanted it. And to make matters even worse, the bridge has to stay balanced at the entire time. So we have actually 2 crews. Matt and I were basically running one side with the foreman on the other side of the structure, and kind of just, working in tandem and making sure that nobody got too far ahead of each other, and working to get the initial spacing that was needed per the construction engineer's calculations. And in the lower right corner, you can see a Dynatension piece of equipment, a tensiometer that at some point you can actually hook it to the cables, slap the cable, the vibration tells you what kind of force you have in it, and then you verify that with the jack liftoff method. So good times. This was a lot more fun. Actually, this picture here is in June and July. It's way more fun to do this in June and July than when we did the post verification, which took place in December. And in Michigan, December is not pretty. So here's the main three guys that did all the yeoman's work on this. And on the left is Greg, our carpenter. In the middle is our foreman, Pat. And on the right is our laborer, Diego, who right after this job was finished, decided to join H&TB as a construction inspector because I think he'd had enough building bridges. All right, so let's get to the move, the good part. On July 6th through the 8th, we were in the process of finishing up the hangars, and the contractor that had said, hey, over the course of a week, 77 semis were going to arrive with equipment. Unfortunately, they all converged on downtown Detroit in the same day, which obviously is not great for Detroit traffic or our project site, but we had to shuffle through it. It took us 3 days to shuffle through 77 semis worth of equipment just to move the bridge. So first process in the move is these A-frames, these temporary abutments have been in place for 3 years, and we need to park an SPMT right where they're at. So how do we get that out of there to the picture on the right where we just set it next to the dumpster to be recycled? Well, that's where these carrier beams that Matt showed you earlier come into play. They allow us to put the load front and back of the knuckle, and then using walking jacks on the side, we can lift the structure. It actually had to be elevated 16 feet in the air to be able to get the SPMTs under it. And we're obviously not that height yet. So how do we do that? Trees, lots and lots of trees. This is African azobe wood. It's considered an endangered species now, not at the time the blocks were made. It can handle, I believe, 17 tons per square inch. And they store it in an oil to help it stay preserved, because obviously as an endangered species, they're not going to be able to go get more of it anytime soon. This is what it looks like when it arrives on our job site. And I believe we ended up having maybe 2.5 flatbeds, semis full of those crates for all the blocks, because each corner needed, significant amount of lumber. You can actually tell from the Jenga blocks that are on the right, the darker ones with the red ends, that's the African azobe. And the other ones are a new material they're using. It's a bamboo epoxy hybrid, are the green lighter colored ones. But they kept telling us not to touch the azobe without gloves on. And I assume that just meant, I asked, is the wood really that hard to get a splinter out or something? And their answer was no. The chemicals we stored in so that to keep it preserved will kill you if you get it in your skin before we can get you to the hospital. So you probably don't want that stuff in your body. All right, so once we got them up in the air, we got the A-frames cut out. It dawned on us, this is the first time we've seen the sole plates in 3 years, and it's the last time we're going to see them with any kind of room to work on them ever again. So the contractor decided to take this opportunity to grind off the galvanizing so that we could weld the bearings in place. Again, how everything on a structure of this size, everything's multiplied in time. Contractor thought it'd be an hour for their crew to take all 4 plates out, and after a few hours on the first plate, they still had 11 mils of galvanizing to get rid of. So we were there for an entire day with multiple crews just to get that small area ground out. Here we are on the 15th. We are now ready, and the SPMTs to pull in there. And I think this is just a great picture from that parking structure. During the initial design, original estimates for the weight of the structure called for probably 80 lines of SPMTs. By the time we got the numbers kind of refined, we were up to 96. And at the end of the day, for stability and things like that, we ended up using 120 lines of SPMTs, which means Mammoet was the only company in North America that could actually handle this work without having to borrow equipment from other contractors. That just tells you the sheer magnitude of what we were doing here. And so there you can see all the SPMTs, and they're getting assembled at that point. It's just a great picture to show you how much equipment we needed. And then on the right, you can see them pulling into each of the 4 corners, preparing to be loaded. So on the 16th, this is when we loaded the SPMTs. We actually began to play Jenga in reverse and slowly walk them down until they were loaded on each of the shoes. Now, technically, each shoe has enough force in the 2 jacks inside of it to actually handle each corner on their own. However, we did have a stability question come up during design. Is the shoe going to be able to handle the amount of force that's going to be implied on it when it's for braking force, and also stability making the turn to the abutment? Eddie He from Parsons is a very brilliant man, asked a very brilliant question, and the response we got was, when we asked how does this shoe work, the response we got from the contractor was, it just does. As you can imagine, engineers, and just does is not really a calculatable answer. So once again, compiled a group of engineers and came up with the idea of the carrier beams. These carrier beams were no longer just for the initial lift. They were going to get to make the ride with us. At which point we then figured we better get them tied down. So on the 16th here, we spent the rest of the day just putting chains, come-alongs, pulleys. I think we went and got every chain in the Metro Detroit area to tie this together to make it as stout as possible. And then also we had to make the realization that the rear carrier beams on the front abutments, the north abutments, or the north knuckles, was not going to be able to make the trip, or to be able to be removed and then replaced. It was going to have to make the trip with the bridge. So the picture on the right, there we are, chain pulleys, and we are actually anchoring those to the knuckles so that they can make the transfer with the bridge. All right, so Matt brought up the monitoring system. As you can see, the picture on the right, believe it or not, that monitoring system is fully installed. And if you're asking yourself, I don't see any wires, well, neither did we, and that's why we tripped over them and broke them quite a few times. But most importantly is that little red light. That little red light had more billable hours during the move than anything else. As a group of grown men and women, engineers from some of those intelligent engineers in the entire country, spent the entire move staring up like turkeys looking into the rain, waiting for the little red light to go off, where we all screamed, stop. All right, so the first move began on July 19th. Now to moving a 5 million pound bridge is just another day at the old work site. But for the entire Michigan Department of Transportation and all of our consultants and contractors and the people who've seen this thing sitting there for multiple years, wondering when it was ever going to move, we were very, very excited. We were so excited that we have multiple pictures of the giant rat that ran out of the equipment when we fired up the power packs. So we're not sure which state that rat made its move in here from, but we now have a new resident in the city of Detroit. All right, so the first move is obviously going to go down, and then we have to turn about almost 90 degrees to face up with the abutment for 94. It was at this point we realized to get those front carrier beams off, we needed to have room for a crane, and our work site bridge staging area was not big enough. At the last minute, we had a geotech say, well, let's just pile gravel on the grass until it can't take it anymore. That should hold the end of your bridge. We, again, as engineers, said, maybe we should put some, maybe we should take out the topsoil of the grass. We'll throw some geotextile, some stone, and some crane mats down and give us some room to back up that SPMT. So that's exactly what we did here. And you can see now that this red square is off of the BSA. And to make matters worse, if you'll notice, the building we were going to back up to the front doors of was the Wayne State University Law School. So if you can imagine, the worst place to park an SPMT is in the lobby of a law school. Made everybody a little nervous, but if we were able to bring the power packs up to a vertical position, and we were able to get it to fit just ever so slightly. So here's the crane coming to the front. We're going to pull those front carrier beams off, and then we pulled up to the abutment on the right. You can see the picture where the slide rail system is waiting to transfer the skid shoe from the front SPMTs to the south abutment. And that's exactly what we had to do. So we had to wait, obviously, for our closure time, which is the following Monday. We closed on Sunday and started putting down a stone. And so on the 23rd, we begin the initial handoff. And again, everyone wants to take the pictures of the 5 million pound skeleton crawling across the parking lot, but ask any of the engineers that know what's going on. And this is the most nerve-wracking part, is handing this thing off to an abutment back to an SPMT. It's not only just a slide, it is one of the most unique slides you will ever see in bridge movement. So very complicated, multiple crews. And of course it's skewed and nothing else, all these blocks are square, but the bridge is skewed and at weird angles. So basically the shoes did not make their transfer at the exact same time. So there's a lot of stopping and shimming. And I mean, you're not shimming with a small shim, we're shimming with giant steel, half-inch road plates type of a thing to get everything lined up. And so it took us an entire day to transfer to the 34-foot tall towers on SPMTs down on the freeway below. Those are your front SPMTs that were disassembled and moved down over the weekend. So now all that, an entire day just to get us into what you see on the left and on the right there. The rest of the day was spent with, as you can see, all the chains and come-alongs again, all the control lines for the different hydraulics, all of the monitoring systems. Everything had to be basically replaced and set on there and reinstalled. The beams, the carrier beams that made the transfer with the bridge had to be reinstalled. So just an entire day of working on that kind of stuff. That night, the state of Michigan, our weather here is well known for being temperamental. I decided to, for out of nowhere, dump enough water to flood parts of 94 on us. And so now we've added another level of difficulty. We have half of our bridge 34 feet in the air. It absolutely has to move today. And now we have to road plate the entire process. And of course, we didn't have nearly enough road plates. So now we're going to have to play hopscotch with road plates while we worry about our bridge 34 feet in the air. Here's some great pictures of that move as we come across I-94. You can see the road plates and the loader down below moving them around. Lots of stopping and going. On the right, you can see the rear SPMTs. They're still just hanging out at the behind the south abutment, just waiting to do their jobs. So on the 25th, we are now ready to do the second transfer or handoff. Again, this is complicated because of the skew and the angles and everything, and the unique geometry of each of the knuckles. With each stroke of the jack, with the loading condition changed for one of the four corners. And so we're not just transferring the two north knuckles at the same time, and all four at the same time. It literally, with each stroke of the jack, one of the four corners was shimming, yelling, changing, calling out, orders to each other. It's just a very long process, but again, it's the most unique part of the job is the handoffs. So again, we handed this one off onto the abutments on the 25th, and then we have to lift it off of the SPMTs so we can pull them out. So here's our Jenga blocks are back and our walking jacks, and we've set everything up again, braced off of the abutments, and jack stands on the abutments themselves. And then on the 26th, we were able to pull out the SPMTs and begin the lowering process. Now this is where it gets fun again. The initial design is plenty of room as far as the engineers were concerned for spatial issues. However, the walking jacks availability for the size we needed would not fit. So as we're doing this, we're also still trying to figure out how we're going to make the final transfer as we get closer to the bottom. You can see here, we're getting lower and lower towards the substructure. But as you can imagine, the bottle jack doesn't act, or the walking jacks don't actually fit between the abutment and the end diaphragm. So here you can see now as we're getting towards our final, even with those at the bearings, we still needed 12 inches of block to get the walking jacks out. So how do we accomplish this? How do we transfer the load back and forth one more time if our jacks won't fit? I'd like to introduce you to the Franken jack. At the last minute, this was the design using 4 foot by 4 foot, I think 2.5 inch, now that I think about it, plates with 6 200-ton jacks chained in between each set to create the Franken jack that would fit underneath the end diaphragm and allow us to transfer load back and forth layer by layer until we worked out the last few layers of block. And there on the right, you can see that the bearings have finally come in contact with the sole plates. And you'll notice it's a little bit discolored. The welds are only going in the front half of the bearing. And so the back half, we just want to make sure we had sealed the area we ground. This was a design change. Again, 3 years in, and we were still figuring out the bearing situation going into the move. So things were kind of in flux there. So the last step was to find the skinniest welders we could to shove them between the knuckles and the abutments. And they were able to then coat and paint the galvanizing and then weld the rest of the perimeter. So one of the things that everyone learned from FIU is there was a number of phone calls that went unanswered, a number of emails that went unresponded to, a number of voicemails that went unchecked. We were decided, and that all came down right as this project was being let. MDOT decided that was not going to be our problem. The people in that circle there are not just onlookers and staying, gawking at the project. We required representatives from MDOT's local office, MDOT's Bureau of Bridges and Structures, HDR, Tetra Tech, H&TB, Parsons, Z Contractors, Jansen Spons, Mammut. All the major players had to have representatives on site at all times during the move. And what this meant was every time a decision had to be made, every time an adjustment had to be made, every time the red light came off, every time numbers came in from the total station, from the monitoring system, everyone was on site in a group making decisions together. And until the entire team concurred, nothing changed. And of course, once we had concurrence, a thumbs up was given. Sometimes it was a different finger, but most of the time it was a thumbs up. And we were able to advance the project and successfully achieve our goals without getting anybody hurt. And then last but not least, right before it went down, we did take a moment for a photo op where every inspectors and engineers, you can see Matt and myself on the far right, Mike there in the first person on the left. And we basically just signed this bridge so that when our great grandchildren matter, Mike.
John, we're losing your sound.
Yeah, hopefully you guys can still hear me. And, but yeah, John, we started to lose you there right at the very end here.
Go ahead, Matt. Just take it from here.
All right. Well, timed out well. That was just the end of John's section. Thank you. So just try to wrap this up here. I know we're at the top of the hour. Just some conclusions. So just kind of some high level things. Accelerated bridge construction projects, even if it isn't for a complex bridge, but really, we just would recommend looking at an alternative delivery concept. I mean, this one was design bid build, although really when it came down to it, it was really, especially in construction, was behaving a lot like a CMGC. The contractor who built this one as the prime was local to Michigan, had never done anything like this. And a lot of the challenges that we had along the way, as John was describing, really, a lot of it just came down to, just their inexperience with this. And even, welding the bearings, I mean, that would already, we'd already made a change to do it the initial way they'd wanted to. And then they came back right before and said, oh, we can't do that. So, just, it was that constant, collaborative team effort with them that really, helped, I'd say, get the project done, but also, maybe going that direction from the start might have, had some efficiencies there. Also, one other thing, John talked a lot about the mock-up. That was really a great thing to do. Again, everyone gets better with practice, no matter what it is. And certainly it's something like this that the contractor's never built anything like it before. That was a very big cost savings and benefits to the project. Again, I'll say the independent peer review is very valuable. Just anytime someone's been staring at a certain project for, months, if not years on end, just bringing in that outside set of eyes is, really can, give you new ideas, shed light on things that maybe just kind of gotten lost, when you really, working hard on a project. So definitely would recommend that, any complex bridge project. And again, just that final point, just that collaboration, a lot of us got to be very good friends through this process too, but just, everyone, really credit to the whole team. Everyone checked their egos at the door. Everyone tried to add value and just really work together. Any idea was a good idea, and worth listening to. And again, I can't understate really how valuable that was to the whole project. So just finish up. These are some aerial shots they were taking. These were taken last fall, right before the snow started flying. The bridge is actually open to traffic now, although it's not quite done. There's still some minor cleanup work that's going to happen once the weather warms up here in Michigan later this spring. But you saw the renderings.
Matt, flip back to that last picture.
Oh,
I just wanted to point out the recording studio and how close that really is to the end of the bridge.
Yep, it's right here with the blue roof. So yeah, if you want to, we showed the renderings earlier. This is what it actually looks like when it was all said and done. And once, again, the planting season and everything happens later this year, all that nice landscaping and park-like structure will be completely finished. And with that, I guess if there's still time, you guys can hang on for a minute. We can take any questions.